Some important features are only important because the chart is lying. We will use permutation importance in Python to measure what truly matters. If your model tells you a feature is important, but you do not trust it, this video fixes that. You will learn how to test a feature by breaking it and watching the model fail. By the end, you will be able to say which columns really move the needle, not just which ones are correlated with the label. I keep things simple and hands-on. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Permutation importance is a practical way to answer one question. If I randomly shuffle this column, how much worse does the model get? That tells us how much the model actually relied on that column to make predictions. People reach for permutation importance when correlation and coefficient size are misleading, or when models are complex and internal weights are hard to interpret. Success means you can rank features by the real impact on predictive quality, not by spurious signals. At a high level, the idea is easy. Train a model on your normal data. Then take one feature at a time, shuffle its values in the validation set, and measure the drop in performance. Bigger drops mean bigger importance. This is robust because it measures the model behavior on held-out data, not just training statistics. It also catches redundant features. A duplicate column can look important in a correlation table, but swapping it will show the true joint effect. We will build a small correlated dataset, fit a simple linear model, and walk through 3 diagnostics: correlation ranking, baseline error, and permutation impact. Then we will add a twin feature to show how permutation importance treats redundancy. No heavy math, just experiments you can run and trust. Now we will create the toy data and fit a model. This snippet builds a tiny correlated dataset and a simple linear model. It first creates a handful of feature columns where some features are linear combinations or noisy variants of others. Then it creates a target that depends on a subset of those features plus noise. The data is split into training and test sets so we can measure out-of-sample error. Finally, a plain linear regression model is fit on the training data. The key idea is to make a controlled example where correlation and true influence are not identical, so we can later show how permutation importance separates the two. Next, we will compute a baseline error and set up a quick correlation check. This snippet measures baseline error and defines a quick correlation helper. It evaluates the fitted model on the test set and reports a baseline metric, commonly mean squared error, which measures average squared difference between predictions and true targets. The snippet also defines a small helper that computes the Pearson-style correlation between each feature column and the target in the test set, so we can see which columns are simply correlated with the label. The baseline error is the reference we will compare against after shuffling features. And the correlation helper shows how naive ranking by correlation can mislead when features are interdependent. Now we will rank features by simple correlation to see what that naive chart shows. This snippet ranks features by correlation to show a misleading ordering. It computes the correlation score for every feature against the test target, sorts them, and prints the ranking. In our constructed data, you will see that features which are noisy twins or proxies for the true signal can show up near the top, even though the model might not depend on them uniquely. The core lines read each test column, compute the correlation score, and then sort by absolute value. This is useful to contrast with permutation importance because it highlights how correlation measures association, not causal or predictive contribution. Next, we will apply permutation importance to measure impact directly. This snippet applies permutation importance to see which swap hurts most. For each feature, it makes a copy of the test set, randomly shuffles that one column so its relationship to the target is broken, then scores the model on the modified test set. The importance is the increase in error relative to the baseline. The snippet repeats the shuffle process multiple times and averages results to stabilize the estimate. Important knobs are which performance metric you use and how many repeats you run. More repeats give less noisy results, but cost more computation. This procedure tells you the actual contribution of each column to predictive performance. Finally, we will add a duplicate feature to test redundancy handling. This snippet adds a redundant twin feature to prove permutation robustness. It duplicates one of the original columns, so the dataset now contains a pair of highly correlated twins. The code then reruns the correlation ranking and the permutation importance routine. Correlation ranking will typically show both twins as strong, which looks alarming. Permutation importance, however, reveals the true effect. Swapping one twin might not increase error much, because the other twin still carries the signal. And only when both are disturbed does the error jump. This proves permutation importance, exposes shared contribution, and handles redundancy in a way plain correlation cannot. Mapping this toy experiment to a real project is straightforward. Use the same pattern on a validation set for your production model. If you have many features, run permutations in parallel and compute confidence intervals by repeating shuffles. This scales from debugging a dozen columns to auditing a production pipeline with many engineered features. Recap. Permutation importance measures the drop in model performance when a feature is shuffled. Use it when correlation or coefficients mislead you, or when you need behavior grounded in held-out performance. Caveat. If features are highly correlated, you may split importance across them, so interpret grouped effects carefully. Next step. Scale this approach to a larger feature set and add cross-validated permutations so you get stable importance across multiple splits. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.